across the three spatial dimensions that define the geometry of human experience. Every object, every structure, every configuration of matter extends through precisely measurable coordinates of length, width, and height, creating the familiar landscape of physical reality where distances can be traversed by moving forward or backward, left or right, up or down, the entire accessible universe appearing to consciousness as a three-dimensional manifold, embedded in the flowing stream of time that carries all events from past through present toward future, in a seemingly inexorable progression that permits memory but forbids return. Within the mathematical framework of geometry, however, a fourth spatial dimension exists as a logical extension of the coordinate system, perpendicular to all three familiar axes simultaneously, in a direction that cannot be visualized through human spatial intuition, yet remains perfectly consistent within the formal structure of mathematics, where four-dimensional objects called tesseracts or hypercubes possess 8 cubic cells as boundaries, just as three-dimensional cubes possess 6 square faces, and where rotations can occur in 6 independent planes, rather than the 3 planes accessible to objects confined to three-dimensional space, each additional dimension multiplying the possible configurations and transformations available to geometric forms by factors that grow combinatorially with dimensional count. The question implicit in recognizing this mathematical possibility, this geometric reality that exists in the abstract realm of pure mathematics yet finds no obvious manifestation in the physical world of human perception, concerns what transformation in consciousness, what revolution in sensory capability and neural processing, what evolution in the fundamental architecture of perception and cognition might enable organisms evolved in three-dimensional space to apprehend and navigate a fourth spatial dimension, and furthermore what cascading consequences would follow from such an expansion of accessible reality, as beings capable of four-dimensional perception would inhabit a superset of three-dimensional space, able to observe and interact with familiar three-dimensional structures from vantage points literally outside the three-dimensional manifold, viewing them from directions that cannot be expressed as combinations of forward-backward, left-right, or up-down movements. The physiological mechanisms required to perceive a fourth spatial dimension would necessitate radical restructuring of the sensory apparatus and neural processing systems that construct spatial representation in the brain, as human vision operates by detecting photons arriving from various directions within the three-dimensional space surrounding the observer, each photon's trajectory describable by 3 spatial coordinates and the 2 angular parameters of spherical polar coordinates that specify direction within the familiar three-dimensional framework. The resulting 2-dimensional retinal images then processed by visual cortex areas that extract features, construct depth perception through binocular disparity and motion parallax, and ultimately generate the subjective experience of inhabiting a three-dimensional environment. The extension to 4-dimensional perception would require either the detection of photons propagating through 4 spatial dimensions, implying that light itself possesses a 4th spatial degree of freedom currently invisible to three-dimensional detectors, or alternatively the development of entirely novel sensory modalities that respond to physical fields or forces existing only in the extended 4-dimensional space, perhaps gravitational gradients that vary in the 4th dimension, or quantum fields whose excitations carry information about 4-dimensional structure invisible to electromagnetic radiation, confined to 3-dimensional propagation. The neural architecture supporting 4-dimensional spatial perception would necessarily exceed the complexity of existing visual processing systems by substantial margins, as the human visual cortex already dedicates approximately 30% of cortical volume to processing 3-dimensional spatial information, implementing hierarchical feature detection, coordinate transformations, and spatial memory systems whose computational demands scale with the dimensionality of the represented space, suggesting that 4-dimensional perception would require either dramatic expansion of neural tissue devoted to spatial processing or revolutionary improvements in neural coding efficiency that compress 4-dimensional information into neural representations comparable in resource requirements to current 3-dimensional processing systems. The mathematical preparation for understanding 4-dimensional geometry would begin with systematic exploration of lower dimensional analogies, examining how 2-dimensional beings confined to a plane would perceive 3-dimensional objects passing through their planar universe, seeing only the 2-dimensional cross-sections that intersect their plane at any given moment, a sphere appearing first as a point, then expanding to a circle of maximum radius as the sphere's equator crosses the plane, then shrinking back to a point before vanishing entirely as the sphere completes its transit. The two-dimensional observers inferring the three-dimensional structure only through analysis of how these cross-sections evolve over time or through mathematical reasoning that extends their geometric framework beyond direct perceptual experience. By analogy, three-dimensional beings would perceive four-dimensional objects as three-dimensional cross-sections that evolve as the four-dimensional object moves through three-dimensional space in the fourth dimension, a hypersphere appearing first as a point, then expanding to a sphere of maximum volume before contracting and vanishing, the four-dimensional structure inferable through careful measurement of how these three-dimensional sections transform, and through application of mathematical principles that extend familiar geometric relationships into four-dimensional space. The rotation of four-dimensional objects would produce even more striking effects, as a tesseract rotating in the plane containing two of its four-dimensional axes would appear to three-dimensional observers as a continuously transforming three-dimensional structure, its cubic cells seeming to fold through each other in ways that violate three-dimensional geometry, edges passing through faces and vertices emerging from solid volumes. The entire transformation resembling impossible geometry, yet representing perfectly natural four-dimensional rotation projected into the three-dimensional subspace of direct observation. Within the physics of four-dimensional space, assuming the existence of a genuine fourth spatial dimension rather than the time dimension of special relativity, the fundamental forces and fields of nature would necessarily extend into the additional dimension, gravity obeying an inverse cube law rather than inverse square law, as gravitational field lines spread through four spatial dimensions instead of three, diluting more rapidly with distance and requiring recalibration of orbital mechanics, stellar structure, and cosmological evolution to account for the altered strength of gravitational binding at all scales from planetary systems to galactic clusters. Electromagnetism would similarly extend into four dimensions, with electric and magnetic field vectors acquiring additional components and the geometry of field lines adapting to four-dimensional propagation, potentially allowing magnetic monopoles as topologically stable configurations in four-dimensional space where they cannot exist in three dimensions, and enabling electromagnetic radiation to polarize in three independent directions rather than the two polarization states available to light in three-dimensional space. The quantum mechanics of particles in four-dimensional space would exhibit modified properties, with the uncertainty principle relating position and momentum in four spatial dimensions rather than three, orbital angular momentum quantum numbers taking on different values as rotation planes proliferate with dimensionality, and the periodic table of elements potentially expanding or contracting as atomic orbital structure adjusts to four-dimensional geometry, perhaps stabilizing elements that decay rapidly in three dimensions, or destabilizing elements that remain stable in familiar three-dimensional chemistry. The entire landscape of possible chemical compounds, shifting as bonds form in directions inaccessible to three-dimensional molecular geometry. The biological implications of existing in four-dimensional space would extend far beyond sensory perception to encompass fundamental questions of organism structure, as bodies evolved for three-dimensional environments would face challenges of mechanical support, circulatory system routing, neural connectivity, and organ arrangement when extended into four dimensions, the surface-to-volume ratio scaling differently with organism size and potentially requiring modified strategies for gas exchange, nutrient distribution, and waste removal compared to three-dimensional organisms. The topology of four-dimensional organisms would permit configurations impossible in three dimensions, with digestive systems potentially forming closed loops without any external opening as the intestinal pathway curves through the fourth dimension to connect mouth and anus through four-dimensional space, while remaining topologically sealed from the external environment in any three-dimensional cross-section, or circulatory systems forming complex knots that distribute blood without any vessel crossing another, exploiting the additional degree of freedom to eliminate the need for capillary beds to connect arterial and venous circulation. The immune system and cellular organization of four-dimensional organisms would operate under different geometric constraints than three-dimensional life, with cells possessing additional surface area relative to volume, and potentially supporting higher metabolic rates, though thermal regulation would face challenges as heat dissipation scales with surface area, and the altered geometry of four-dimensional space might accelerate cooling rates for warm-blooded organisms or complicate the maintenance of temperature gradients necessary for biochemical function. Surrounding the individual scale of organism structure, the ecology of four-dimensional environments would exhibit dynamics fundamentally distinct from three-dimensional ecosystems, as predator-prey relationships would operate under different geometric principles when organisms can move and hide in directions inaccessible to three-dimensional movement, a prey organism potentially evading a predator by moving perpendicular to all three familiar dimensions, escaping into a region of four-dimensional space where the predator cannot follow if it lacks the sensory apparatus or locomotive capability to navigate the fourth dimension. The architecture of four-dimensional habitats would permit structures impossible in three dimensions, with buildings potentially containing rooms that appear disconnected when viewed from three-dimensional cross-sections yet connect through four-dimensional corridors, or dwellings that achieve enormous internal volumes while occupying minimal space in the three-dimensional subspace observable to beings lacking four-dimensional perception. The entire geography of four-dimensional worlds permitting landscapes where travelers can journey between locations without passing through the intervening three-dimensional space by routing their paths through the fourth dimension. The physics of four-dimensional materials would determine the mechanical properties of structures built in this extended space, with materials potentially exhibiting greater tensile strength as atomic bonds extend through an additional dimension, or conversely becoming more brittle as the additional degree of freedom permits crack propagation along new failure modes inaccessible to three-dimensional fracture mechanics, the engineering principles governing architecture and manufacturing requiring complete reformulation to account for stresses, strains, and failure mechanisms operating in four spatial dimensions. Beyond the scales of individual organisms and their immediate environments, the astronomical implications of four-dimensional space would transform every aspect of cosmic structure and evolution, as stars would burn through their nuclear fuel more rapidly under the intensified gravitational fields produced by inverse cube law gravity, shortening main sequence lifetimes and potentially making long-term stellar stability more difficult to achieve, though the altered geometry might permit alternative pathways to gravitational equilibrium that have no three-dimensional counterparts. The formation of planetary systems in four-dimensional space would follow modified dynamics as protoplanetary disks extend into the fourth dimension, potentially forming three-dimensional hypersurfaces of matter rather than two-dimensional disks. The accretion processes that gather material into planets operating under different collision geometries and gravitational focusing effects, possibly producing planetary systems with exotic architectures where planets orbit in paths that loop through the fourth dimension, or where multiple planetary systems share the same three-dimensional space while remaining separated along the fourth axis. The large-scale structure of four-dimensional space itself would extend beyond the familiar cosmic web of three-dimensional cosmology, with galaxy filaments potentially forming three-dimensional sheets or volumetric structures rather than one-dimensional threads, voids occupying four-dimensional volumes rather than three-dimensional bubbles, and the topology of the cosmos possibly containing features without three-dimensional analogues, such as four-dimensional handles connecting distant regions of space through wormhole-like structures that exist naturally in four-dimensional topology rather than requiring exotic matter or extreme space-time curvature. The navigation of four-dimensional space by beings evolved in three dimensions would require the development of conceptual frameworks and cognitive strategies that translate four-dimensional geometry into forms comprehensible to neural systems designed for three-dimensional spatial reasoning, much as three-dimensional navigation currently employs maps that project three-dimensional geography onto two-dimensional surfaces using various coordinate systems and projection methods that preserve some geometric properties while necessarily distorting others, the choice of projection depending on the navigation task and the regions of space being represented. Four-dimensional navigation systems might employ three-dimensional volumetric displays that evolve over time to represent the fourth dimension as a sequence of three-dimensional sections, allowing navigators to apprehend four-dimensional structure through systematic exploration of how three-dimensional cross-sections change as one moves through the fourth dimension, or alternatively might develop abstract symbolic representations that encode four-dimensional relationships in formats accessible to three-dimensional intuition, trading direct geometric visualization for algorithmic or algebraic descriptions that support calculation of four-dimensional trajectories and obstacle avoidance without requiring complete perceptual comprehension of the four-dimensional environment. The cognitive load of four-dimensional navigation would likely exceed that of three-dimensional spatial reasoning. As the number of possible rotations increases from 3 independent planes in 3 dimensions to 6 planes in 4 dimensions, each rotation potentially transforming a 4-dimensional object into configurations that appear dramatically different when projected into 3-dimensional observation space, requiring navigators to maintain mental models of how rotation in various planes alters the observable 3-dimensional appearance of 4-dimensional structures and landmarks. The philosophical implications of accessing a 4th spatial dimension would extend beyond technical questions of perception and navigation to encompass fundamental issues about the nature of reality and the relationship between mathematical possibility and physical existence, as the geometric consistency of 4-dimensional space within mathematics has been established for more than a century through the work of Bernhard Riemann and subsequent geometers, yet physical space appears to possess only 3 large spatial dimensions, with no observational evidence suggesting the existence of additional macroscopic spatial dimensions beyond the 3 that humans directly perceive. The relationship between the mathematical abstraction of 4-dimensional geometry and hypothetical physical 4-dimensional space would raise questions about whether mathematical existence implies physical existence, whether all logically consistent geometric spaces must correspond to possible physical realities, or whether the apparent 3-dimensionality of space represents a fundamental constraint of physical law rather than an accident of human evolution or perceptual limitation. String theory and related approaches to quantum gravity propose the existence of additional spatial dimensions beyond the 3 large dimensions of everyday experience, typically 6 or 7 compact dimensions curled up at scales smaller than current experimental resolution, suggesting that space may indeed possess additional dimensions invisible to macroscopic observation, but detectable through high-energy particle physics experiments or precise measurements of gravitational inverse square law deviations at submillimeter scales. Though these proposed extra dimensions differ qualitatively from the large 4th spatial dimension implied by hypothetical 4-dimensional perception and navigation, being instead compactified dimensions accessible only at energy scales far exceeding those of ordinary matter. The historical development of human understanding of dimensionality traces a progression from implicit assumption of 3-dimensional space through explicit geometric formalization to abstract generalization beyond perceptual dimensions, as ancient geometers worked within 3-dimensional space without recognizing dimensionality as a variable parameter. Medieval scholars occasionally contemplated the logical possibility of additional dimensions without developing systematic mathematical frameworks for their description, and 19th century mathematicians finally constructed rigorous theories of n-dimensional geometry that apply consistently for any positive integer n, demonstrating that geometric reasoning need not be limited by the 3 dimensions of physical space, but can extend to arbitrarily many dimensions while maintaining logical consistency and supporting meaningful theorems and constructions. The cultural impact of recognizing dimensional generality extended beyond pure mathematics to influence philosophy, fiction, and popular imagination, with Edwin Abbott's 1884 novella Flatland presenting dimensional analogy through the story of a 2-dimensional being encountering 3-dimensional reality, using geometric allegory to explore social hierarchy and the limitations of perspective, while 20th century science fiction frequently employed higher dimensions as plot devices, enabling faster-than-light travel, parallel universes, or exotic physics that transcend 3-dimensional constraints. The actual development of technologies or biological modifications that would enable 4-dimensional perception and navigation would require not merely mathematical understanding or fictional speculation, but rather concrete physical mechanisms for detecting and responding to a genuine 4th spatial dimension, assuming such a dimension exists at macroscopic scales, or alternatively for generating perceptual experiences that simulate 4-dimensional geometry within neural systems evolved for 3-dimensional processing, creating virtual 4-dimensional environments through computational means, even if physical space remains fundamentally 3-dimensional. Across all possible scenarios for 4-dimensional perception and navigation, from genuine extension of physical space into a 4th large dimension to sophisticated virtual reality systems that simulate four-dimensional geometry within three-dimensional physical substrates, the fundamental transformation would involve expansion of the accessible space of configurations, as four-dimensional movement permits trajectories and manipulations impossible within three-dimensional constraints. Objects can be rotated into orientations unreachable through three-dimensional rotation, and the topology of connections between regions changes as the additional dimension permits paths that avoid three-dimensional obstacles or barriers that remain impassable without four-dimensional navigation. The gradual adaptation to four-dimensional existence would proceed through stages of increasing facility and intuition, beginning with mathematical comprehension of four-dimensional relationships through analogy and calculation, progressing through perceptual training that builds four-dimensional spatial intuition by systematic exploration of how four-dimensional objects appear when projected into three-dimensional observation space, advancing through motor skill development as beings learn to navigate and manipulate objects using four-dimensional movement capabilities, and eventually achieving native four-dimensional competence comparable to the unreflective mastery of three-dimensional space possessed by organisms evolved in three-dimensional environments, though whether such complete naturalization of four-dimensional spatial reasoning could occur within neural architectures shaped by evolutionary pressures in three-dimensional space remains uncertain, depending on the plasticity of spatial processing systems and their capacity to reorganize around expanded dimensional structure. The ongoing exploration of four-dimensional geometry, whether through pure mathematics, physical experimentation searching for evidence of extra dimensions, or virtual reality systems that simulate higher dimensional navigation, continues to expand human comprehension of geometric possibility and the relationship between perceptual limitation and mathematical reality, demonstrating that spaces far stranger than everyday three-dimensional experience remain accessible to systematic investigation, and that the boundaries of human understanding extend beyond the constraints of direct sensory perception into realms that can be apprehended through reason, calculation, and the patient construction of conceptual frameworks that translate abstract structure into forms comprehensible to minds evolved within the particular dimensional configuration that characterizes the physical universe as currently observed.